take a look at strategies of integration using a method of completing the square to write the integral. So what we've been starting to look at are issues where u substitution just does not work. And really in our case here, there is no u to choose. Because if you choose the denominator, you're going to end up with an x to cancel out with nothing. All right. And we also can't divide a larger denominator into the smaller numerator to rewrite the integral. So another strategy is using completing the square. So a lot of times with these, to keep in mind, we're going to end up seeing like those arcsine or arctangent problems where we're integrating those fractions. So a couple things for you to keep in mind is it's that denominator that we're going to try and rewrite. Now, I think it's not really, so it's kind of similar to the idea of u substitution, but it's not u substitution. So I'm going to use a different letter. Let's say we use the letter z, or really any letter is fine as long as it's not an x. So I'm going to take that denominator. I'm going to say, okay, well, z equals that entire thing, x squared plus 6x plus 10. And what we're going to do is we're going to rewrite this equation using completing the square. Now, when we complete the square, what we do is we separate the x's with all other values. So I'm going to subtract that 10 over to the other side. So I have z minus 10 equals x squared plus 6x. Now, when we complete the square, our goal is to add a value to both sides to keep the equation balanced that will create this perfect square trinomial. Now, the way we find that value is we take half of the b term, right? The b term is that middle term next to the x, half of 6, and square that number. So half of 6, we get 3. 3 squared is 9. So we're adding 9 to both sides. Now, once we add that 9, on the left-hand side, we're just going to combine some like terms. I have negative 10 and 9, which gets me z minus 1, equals, and then on the right-hand side, you should be able to factor this thing. And it should always be like, in this case, x plus 3 times x plus 3, which we could rewrite as x plus 3 squared. Now, to kind of finish this process, I'm going to move that 1 back over, and we end up with z is equal to x plus 3 squared plus 1. So essentially what we're saying is that x squared plus 6x plus 10 is the same as x plus 3 squared plus 1. Now, the reason why that helps us is back over here, we're going to integrate this problem. We're going to integrate, instead of 1 over that trinomial, we're going to integrate 1 over x plus 3 squared plus 1 dx. And this thing right here resembles our arctangent function. The only difference is instead of just x, right, it's x plus 3. So when we integrate this function, we're going to end up with the arctangent or the inverse tangent, either way you write it is fine, of x plus 3 plus c. Right? And that's going to be our first completing the square problem. Right, another example of this, sometimes we see similar situations, but all underneath a radical. We're going to take that same approach. Can't use u sub on this one because there'd be nothing to cancel out any of the x's. So then we're going to just try and rewrite this denominator as our completing the square method. So off to the side again, I'm going to say we'll take z, we'll call this z equals negative x squared plus 8x minus 15. Now, one thing with completing the square is the x squared has to be positive. So I'm going to divide everything here by that negative 1. So I have negative z equals x squared minus 8x plus 15. Right, since I have to move that 15 over to the other side, I end up with negative z minus 15 equals x squared minus 8x. Now we got to find out what are we going to add to both sides here. So to complete that square, we take half of the b term, half of 8 is negative 4, negative 4 squared is 16. We add 16 to both sides. So on the left, I have negative z plus 1 equals, and on the right side, I can factor this to x minus 4 squared. All right, I'm going to subtract that 1 back over. So negative z equals x minus 4 squared minus 1. Then I'm going to divide by that negative 1, right? Divide everything by the negative 1 to get the z back. We have z equals negative x minus 4 squared plus 1. Now, I'm going to rewrite this just to kind of make life a little bit easier to recognize the pattern here. But right, our inverse sign has 1 minus, not negative x plus 1, but 1 minus. It's the same thing, but just visually it's going to be a little bit easier to see. So since I finally rewrote this thing, I'm going to substitute this back into my integral. And we could say this integral is the same as me integrating 1 over the square root of 1 minus x minus 4 squared dx. And when we integrate that, that resembles our inverse sine or arc sine of x minus 4 plus c. And we have that final answer. Right? So ultimately, completing the square can help you as well, right? It's another tool in the toolbox to help us integrate. All right, one more problem, and this is where it starts to get a little bit trickier, right? A little bit trickier for us to work with. Okay, so with this integral, a couple things we can do here. One, this 32 up top, we could bring that thing to the front, and we could rewrite this integral as 32 times 1 over x squared minus 4x plus 20 dx. And then we kind of run into a similar area where, okay, well, let's complete the square, right? This denominator, we can't really work with the way it is. So off to the side, we're going to make that z equals x squared minus 4x plus 20. And as we complete the square, right, we move that 20 over, z minus 20 equals x squared minus 4x. We find those blanks, those values we have to add in. So half of negative 4 is negative 2, squared is 4, so we're going to add 4 to both sides. So on the left-hand side, we have z minus 16 equals, then over here on the right-hand side, we're going to have x minus 2 squared. Now this is where one gets a little bit tricky. When I add that 16 over, I'm kind of dealing with a situation where I have my x minus 2, I have my something squared, but I have a plus 16 at the end. And for this to be that arctan function, right, that we might be looking for, I need this thing to be plus 1. So one thing we could do here is we could, ultimately we're going to work on like a little bit of factoring to try and rearrange this thing a little bit, but we'll again take a quick another way we can make this thing equivalent is we could factor out that 16 to the front. Now, when we do that, what happens is this x minus 2 squared is going to have to be divided by 16, and the 16 has to be divided by 16, which is fine because that gives us that plus 1 that we've been looking for. Now, even more interestingly, this 16 doesn't fit our model of something squared plus 1. So that something squared plus 1, we could take this one step further, and we know that 4 squared is equal to 16. So we can rewrite that x minus 2 as x minus 2 over 4 squared plus 1. So this whole thing now is something squared plus 1, and it just so happens to have that 16 out front. Now, that 16 out front is not as much of a big deal once we bring it into our equation here. So we end up with 32 times the integral of 1 over 16 times x minus 2 squared over 4, x minus 2 squared over 4 plus 1 dx. Now, this 16, I'm going to factor to the front again. So we have 32 over 16, right, since that's in the denominator, times the integral of 1 over x minus 2 over 4 squared plus 1 dx. Now again, we now have our arctangent, something squared, right, plus 1 in the denominator. Now what's interesting about this, that 32 over 16 is just going to reduce to a 2 times the integral of, well, we can integrate now. So we're going to integrate our arctangent. Now there's a little chain rule and u substitution happening here. So when we integrate this, we're going to have the arctangent of x minus 2 over 4 plus c. But the one thing we have to kind of keep in mind here is with u substitution, right? When we replace, like I'm gonna do that quick form of u substitution where we just divide by d inner. We can do that when we don't have any x's left over. We have to be able to divide by the derivative of x minus 4, x minus 2 over 4. Now the derivative, if I find the derivative of x minus 2 over 4, I'm really finding the derivative of 1/4 x minus 1/2, which is 1/4. So I have to divide this fraction by 1/4. And when we divide by a fraction, we really just end up multiplying. So we end up with 8 times the inverse tangent of x minus 2 over 4 plus c. So pretty tricky problem on this one. There's a lot of algebraic adjustments and rearranging of this problem to make it fit that arctangent model. But these are some of those more intense and difficult problems that we might run into. So a couple practice problems with these, and hopefully they start to feel a little bit easier. Let me know if you have any questions. I'll see you guys, see you guys in class.